We've seen that acids may be defined as having the ability to donate a proton. Let's look at what happens if there is more than one proton to donate. Thus far, we've only considered acids that have but one proton to donate. There are actually three groups of acids based on the number of protons they can donate. Monoprotic acids would be those like we've considered thus far, with one proton to donate and therefore only one Ka and one pKa value. Diprotic acids have two protons and their corresponding Ka and pKa values. Polyprotic acids have more than two protons to donate. A good example of a polyprotic acid, and one very relevant to biological systems, is phosphoric acid. As there are three protons to donate, there are three pKa values and three equilibria to represent them. As the fully protonated form of phosphoric acid, pictured on the far left, donates each of its protons, the corresponding pKa values increase. This is because the ionized form becomes more and more negative as each of the protons is released. It becomes therefore harder and harder to stabilize the additional negative charges. Note that for each of the three pKa values, there is a corresponding acid and conjugate base pair. We've seen that pH relates to water itself, so what about the biomolecules that inhabit that environment? We see that pH relates very much to the function of protein enzymes like pepsin, trypsin, and lysozyme illustrated here. If we graph enzymatic activity as a function of pH, we find that each enzyme has a pH range of activity. Some have a broader and some a more narrow range. The lesson here is that when it comes to biological systems, pH always matters.